Okay, so we can start with the some quick review, okay, for a power series. So for power series, okay, you will see the series will have not only the integer n that we need to treat as a variable. So we have the x. Okay? So the x means that it will have certain period of interval, which the interval will be converge or diverge. Okay. So the first idea for the power series is by applying the ratio test. Okay. So ratio test, and then we try to simplify the equations. Okay. Simplify the equations, and then at the end of the equations we will have two conditions. Okay. Two statements. Okay. So the one equations with two statements. A statement of the variable x and statement of the n. And remember that in series, because we are going to limit the series itself with the integer, so we take the limit only between n. So we can configure what kind of limit is this, okay? And then if we find that this limit is maybe equal 1, then we can simplify. The answers become this 3 absolute value x, okay? Which means that we can make some conclusion based on the ratio test. Okay? So ratio test, I hope you can you have already familiar with. Okay? So ratio test, it can be less than 1, greater than 1, or equal 1. Less than 1 means that it is convergent. Greater 1 will be divergent, and equal 1 we are not sure yet. Okay, so converge, we take this and we have the interval, and then to check whether we need to include the endpoint or not, we need to check when the x equal the number. Okay, so check the x, and then we find out which one is diverge, which one is converge. So we have finally we have the interval of convergence. Okay, so maybe we can start from giving you example, okay, on the power series. And the idea is we need to make sure that we can find the radius of convergence and interval of convergence for most of the power series. Okay, let me start with let me check. Okay, maybe this series. Okay, two questions. So yeah, these two questions, the questions the same as before. You need to find the radius and the interval of convergence. We find the radius and since we are only having maybe before the long holiday, 1st April, right? Not 1st April. It's Friday, next Friday, and we only have this day, Friday and Monday, so 3 more classes. So within these 3 classes, I try to complete all. I'm glad to having a quiz, but I think I'll just give you the homework, but you need to do the homework. And the homework, actually using the platform that you just name the task and then you click the answer. Like I think the previous semester I did that. I think I just repeat that. Maybe next week, maybe between like maybe 5 to 6 days, and just check in which day was prepared. And the content will be from the chapter 11. If your score is good enough, I think I'm considering to make it as a quiz. if your score is okay. If not, then it's a homework. Okay, so for both questions and for all the power series, the first thing you can do is to check with the ratio test. Check with ratio test. At least to have some conclusion at the beginning, which interval that is converged or diverged. Okay, so we can take the ratio test. Okay, so we expand all the quadratic. Divide by 2n squared plus 1 divided by n and x equal. Okay. Now we can just simplify. Okay, I think for these cases in simplifying the ratio test, you need to at least reviewing how we do the limit, okay, and some algebra operations. If you maybe kind of forgetting some simplifications, okay. I think both of limit and algebra is basically needed most for solving this ratio test. Okay, and then we can simplify. This would be x. This would be 2. Okay, I think we can separate x. This would be x and 2. And the rest, I think I need to simplify. I need to multiply these equations, right? So we will have a cube and a cube, a cube formula. So, and I think I will just separate x and n. So I will take the limit for n, I think infinity, and then take the n cubed plus 2n squared plus 2n. Okay. N cubed plus n squared plus n plus 1 plus n plus 1. Okay. Now by looking at the limit, because the top equation and the bottom equation have the same degree, I think we can just simplify become 1. Okay, so we can conclude this directly become 1. So we will have the ratio test. So based on ratio test, the series converges when less than 1. Okay, so we have from here we have the radius is 2. Okay, the radius is 2. Okay, so we can conclude the radius is 2. And then I think we can just go directly to find out whether when this is equal 1, this is equal to, what will happen. So we will have x equal 2, which means this will be the series will be from n to the power of n plus 1, and then 2 with power of n. Okay. Now the series will be, this is cancel. The series will be n over n squared, sorry, n squared plus 1. Okay, this series is diverge or converge? N over n squared plus 1. Okay, maybe need to have some time to getting used to this series. So n and n squared. If we imagine we have the 1 over n. Okay, I think we can conclude directly this is diverge. Okay, right? This is diverge. If you need more proof, maybe sometimes I know some trouble in exam. If you feel nervous, when you take the comparison test, when you need to prove whether it's less than, maybe you need to prove that this is less than this one. Maybe your mind feels not sure. Then you can just go directly to limit comparison test. So you divide this with this, divide, and then take the limit, and then check the limit. Okay. So this is diverge, and then when x is equal -2, this is the same as this is or maybe I will write in the negative on the front here. Okay. And now, if you're looking here, looking the series, this is the alternate series, right? The alternate series. And we can try to check whether the series is getting smaller. And I think it's getting smaller, right? If you check, just checking some numbers. And then 3 squared. Yeah, it's getting smaller, right? It's getting smaller. And we can say that this is also the limit. Maybe here first. It's getting smaller. And then the limit. It's 0, right? So based on these two, we can say that it converges. Okay, so from these observations, we can take a conclusion that the interval of convergence is -2, 2, and we include -2. Or we can write in terms of this line number. Okay. Okay. Okay, and the other questions I think is easier than the first one, and I think you can get the answer directly. It should be for all x, right? For the second question. So again, similar, take ratio test, take sometimes to simplify. And then if you take the limit, and limit will be 0, right? This limit will be 0. Which means the conclusions will be the result or maybe the ratio test shows that R will be for all x and interval of convergence is from negative infinity to positive infinity, or convergent, you can say convergent for all x. This is also okay. Okay, any questions? Any questions? Any confusions? I hope not, because I believe the power series is much more direct approach finding the radius and interval convergence. The problem is if the questions will ask maybe asking the more analytical questions, which means it doesn't necessarily to be the full series like this one. Maybe it has some another variable that you need to find, like maybe the radius will be having that variable, but actually it's the same thing. Okay? I hope you still can focus on the subject for finding the R and the interval, finding the radius and the interval. Okay, now we move on to the next sections. So maybe I will take some reminder here that maybe from next week, maybe from next week is 28, right? Maybe 20, or maybe from 30 to maybe April 5, April, let's say 5, I will open the like a homework or maybe just test chapter 11 test. This will be online test, and maybe the total time you need to take maybe around 20 to 30 minutes probably. Okay. I will give you more information later on. Okay. Okay, next sections will be discussing the representations of function as power series. Okay. To start, let's consider the series of x with power of n. Okay. If we expand the series, this will be how the series looks like. And since we have ratio, we need to multiply with x, right? We have a ratio, common ratio that is x. And if you remember, when we deal with the geometric series, for the series to be converged, the r should be less than 1, right? So if we take these assumptions and taking into our component of x, then this will be converged if x is less than 1. And we know that from this series that this 1 plus x squared, the sum of infinite for geometric series, this will be 1 minus x. Okay. If you remember the geo series that we have, we have a 1 minus r, right? Okay, this is the sum of infinite series. Okay. Now, if you apply the same or a similar conclusion with our x, then this is what we get. Okay, so this is the first step to actually saying that if we have the 1 plus x squared, we can take this series and make it into a function. So this is a function. So our series can be represented as a function. So we say that this power series, when its ratio is less than 1, this is power series that represent of function 1 over 1 minus x. Okay. On interval, we need to say the interval from -1 to 1. Okay. And then remember that the sum of the series, we can rewrite the sum of the series as a limit of the sequence of partial sums. Okay, if you still remember what we did at the beginning. Okay. So we have a sequence. Okay. So when we deal with the series, let me take you to some illustrations. When you have a series, okay, of the sequence an, which means you will have the sequence, and you have also the sequence of the sum, which means the Sn, right? So when we deal with the sum of the series, we are actually dealing with the limit of the sequence of its sum, which means that if we take sometimes to check our S, maybe take S1, S2, S3, and take it into our graph, we can make a graph that when we increase the n, the graph will be looking more like this 1 over 1 minus x. But you need to observe the graph on this interval, okay? Only this interval. That is, we say that that's convergent, right? Okay. Let me check the graph. Do we have the graph or not? I think I need to go for a while. Oh, wait a minute. Just to check the graph. Yeah, I think one graph is enough. So as n increases, the graph for the Sn becomes better approximation to the function 1 over 1 minus x on interval -1, 1. So we are only looking at this -1 and 1 in this interval. So if we take some time to check our S, which means S2, or maybe we can write the whole thing, what this means. Okay. It means that we have this x with power of n, right? Start from n equals 0. So this will be 1 plus x squared plus x cubed, right? So when we have S1, this means that it's 1 plus x, okay? We have S2, means that this is 1 plus x squared, okay? S3, okay? And the more you increase, the more that the graph will take the approach to this f, 1 over 1 minus x. I think you can try to graph in the GeoGebra, and you need to focus on this interval. At least if you see here, you see that we have the x2, the quadratic equation, right? The quadratic equation for S2. We have an even function. When we increase to maybe S5 like this one, it has odd function, right? Okay. We increase it, S8 is an even function. S11 is going to have an odd. And if you see the graph, we'll have some, it's not really symmetric because it has like a plus. Nah, okay. I hope you can have good conclusions on this 1 over 1 minus x. Okay. But again, the idea behind this the sections is we can represent the series into a function. So that's the idea. So when we have, for example, we have 1 over 1 plus x squared can we find the sum of the series, or can we find the power series for this one? Okay, which means if we know that we have 1 over 1 minus x, that this is equal to x to the power of n, then with the same structure, with the similar structure, we can exchange this functions and then make it into a new power series from this one. So we can take this 1 over 1 minus x squared. Okay. Now we have the same structure, right? We have the same structure, minus. And we have, this is x, become x. Okay. Now we have negative x squared, and we move this into this condition, this structure. So the structure should be the same. So we will have negative x squared with power of n. Okay, or we can take simplifications and make it more nicely done for negative 1 outside, factor out, and then we have x with power of 2n. And then if you want to find the interval of convergence, we can do that. We can find, if we expand this, this will be alternate series. And we see that this is geometric. The ratio is negative x squared. And to be converged, that this ratio, the common ratio, need to be less than 1. or x squared is less than 1, or so interval of convergence will be -1 and 1. Or we can apply the ratio test as we did before. Okay, I think you get the same idea. Okay, so a little bit recap. So power series, finding rates of convergence, finding interval of convergence, which has the x. Okay. And then from those x, you can also represent the series as a function. Okay. Or from a function, we can expand the series and finding the interval of convergence. Okay. Okay, and then another example, another idea. If we have 1 over x plus 2, we want to make this into a series. Okay. First, we can write 2 plus x to make it similar to what we did in the previous one. So your idea, we need to have 1 over 1 minus x, right? This is our wanted structure, and this is the information we have. So first, we need to have 1 here. So we need to factor out 2. Okay, factor out 2. So this is 2, and then 1 plus x over 2. Okay. And thus we need to have minus x. So we need to have minus minus. Okay. Okay. This half we can factor out of the series. Right? We can just focus on this one. So we can take this half outside, and then we have the sum of negative x, right, over 2 with power of n. Now we can have simplifications for negative x over 2. We can have negative 1 with power of n, and then 2 with power of n plus 1. This is x with power of n. Included inside, already included inside. And the series converges when negative x over 2 less than 1. That is so we say that radius is 2, and then the interval of convergence will be -2 to 2. Okay, one more example. Okay, one more example. If we have x cubed divided by x plus 2. Okay, the first thing is we can take this x cubed and we can write the equations like this. Okay. And the 1 over x plus 2 we already did in the previous one. Let me just take some equations here. And take it here. Okay, we will have a short break. Okay, short break. Okay, we are back to the lecture. So whenever you have the, for example, this one, we have x cubed over x plus 2. Whenever you find that the equation can be looked as x cubed and 1 over x plus 2, or you may have encountered this kind of functions later on, we can take this as these two observations. So this 1 over x plus 2 we can take into our series, we can exchange, and then later we can just multiply with x cubed. Okay? So let's exchange the 1 over x plus 2. And take the series. Okay. And then we just multiply x cubed. Okay. We multiply, we can just look at the x. Okay. So we will have and then that's our series. So we will have, this is start from half x cubed plus minus plus minus da da da. Well, if you want, and if you don't like maybe having plus 3 at this x, we can rewrite this if you want, and maybe start from n equal 3. So then we have we need to minus 3, so this will be minus 2, minus 3, we will have n, I think we just n minus 1, that's still okay. As long as it's going to have the similar series. So this 2 is similar, same. Okay, another way to write. Okay, you want to just keep on this one, and okay. If you want to remove this plus 3 and just taking this n, and you can rewrite the series and take the series maybe from n equal 3. Now, I need you to look on the next section, which includes some of the techniques in derivative and integrations. And let me just write the theorem. Okay, let me just write the theorem. If we have the power series, okay, so if power series this is the general form for series. If the power series has a radius of convergence that is r greater 0, okay, then the function f is defined by, so f of x, we need to just expand the series. Where f should be differentiable continuous, right? Because it's differentiable, and continuous on interval, the interval of convergence, that is a minus r and a plus r. And because it's differentiable, let me okay. So we have, if we want to derive the functions, if you look on how the functions will be, if you derive with respect to x, f prime x, this is a constant, this will be 0, right? This will be this c1x, and it becomes c1 because we derive it, and the other one is constant, is 0. And this one will be, we can take this to the front and take some power rule, and the same thing with the cube, before, b5, okay? So we will have the derivative will be c1 plus 2c2, and then this will be x minus a, and then plus, imagine you have the other one at the cube, this would be 3, okay, c3 x minus a squared, and then plus dot dot dot, and then this will be equal to the series itself. Now it starts from 1 because we derive it, so this will be n, cn, and then x minus a, and then n minus 1. Okay. But you can look on how it can be differentiated. How can we derive this math? Okay. So basically, what we did, or what we are going to use for this case, for the derivative, is sometimes the series. If we can think the series here, and we can think like what the series will be when we derive, or what the series will be when we integrate, we can imagine on how we can represent as a function. Okay, so that's actually a method to determine the representation. Okay, so this is the derivative. Secondly, we can also integrate the fx. So we integrate the fx, which means that if this is our f, if we integrate, then we will have plus constant, right? We have a plus constant for integral. So maybe just like c, and c will become x, and then the other one also we can integrate. So this will be x squared, this will be cubed, okay, and so forth and so on. So we can also try to integrate. So getting the constant, and then plus c1x plus. And let me write this c1 as a c0, okay? And let me write this as in terms of x minus a. C1 or this is equal c plus the sum and both of these derivative and integrations we can write. So when we have the dx sum we can write in terms of, so we can factor out the sum and then write the derivative inside. Also, if we have integrations, we can write okay. Now let me just start with some example on how we are going to use this derivative and integrations. If we have 1 over 1 minus x and then squared, now to deal with this 1 over 1 minus x squared, okay, because we only have knowledge for 1 over 1 minus x, okay, we only have that. And we cannot really simplify just by using algebra. We cannot simplify this 1 over 1 minus x squared becomes our 1 over 1 minus x. So we have, let me write, we have this knowledge, right? And so how we can connect these functions with our given information. If we check, okay, from this 1 over 1 minus x, can we derive, can we integrate, can we try some of these two equations? We can try doing that. Okay. So we can try. For example, let me try with writing 1 over 1 minus x and then write so differentiate. Let's differentiate. So d dx 1 over 1 minus x. This will result 1 over 1 minus x squared, right? Because it has a minus, so it should be the same, right? Because it's minus x, so with multiply with minus, so minus it becomes this positive, right? Okay, but you don't get confused. So if you take this as our differentiation of 1 over 1 minus x, then we can take 1 as 0, so plus 1 plus 2x plus 3x squared plus 4x cubed plus dot dot dot, and this will result in n x n minus 1. Okay, so we can have this as our series, or if you want to just playing with the integer and you don't want to have like from 1, maybe you can just stick to 0, then we can just change the n. So we can change into, so we can have this n plus 1 and x to the power of n. Will be the same series, but each one is fine. And from these conclusions, if you want to find like the radius of convergence, that the radius as you see is just 1, right? Okay, now another example. I just take some obvious functions. Okay. Let me write the full question so you know what you are going to do. Find a power series representation for Ln 1 plus x and its radius of convergence. So first, if you look on the ln, okay, the ln, that if you remember, that if we try to derive, this will be 1 over x. Or if we want to derive the function here, this will be 1 over 1 plus x, right? Okay. Now, if we observe 1 over 1 plus x, this is 1 minus x. Or we have this expansions, which should lead that the ratio should be less than 1. So the ln we will get these results by integrating 1 over 1 plus x, right? Okay. So we take the integrations and integrate all the 1 minus x plus x squared minus x cubed plus and then dx. And then we will have x minus x squared over 2 plus x cubed over 3 minus x 4 over 4 and plus and plus a constant at the end. And then we get that this is so if we have this the series here is sum of so we take the integrations and this will be sum so the way we get the series, okay, the way we get the series, you can get the series by looking at this expansion. You can check n equal 1, n equal 2, you can check from n equal 1, or you can check from here, we can take the 1 over 1 plus x and take it into our series, and then the series we can integrate. Like for example from here. So we can get this series and we can also integrate. And we will have the same meaning. So we can have both method or both approach will be similar. Well, maybe it has different form probably, but it has the same series. Has the same series. But we still have a problem with this constant. So what we are going to do is we need to check what's the constant. So we can look on we can check when x is 0. So we put into equations and we will get ln 1 plus 0 is c. So this is ln 1 plus x, right? And then we get that c should be equal to 0 also. So that means that we can just erase the constant. So we get the conclusions for this ln. X minus x squared over 2 plus x cubed over 3. And write into a sum. And the radius of convergence, if you look on the series itself, the radius is just 1. So we considered the 1 over 1 minus x, derivative of 1 over 1 minus x, integrations, especially the 1 over 1 plus x, we integrate become ln. And the other one that is still similar to 1 over 1 minus x is tangent inverse. If you remember tangent inverse, it has relation with 1 over 1 plus x squared, right? So which means we can play with the tangent inverse. Okay. So if we have the tangent inverse, if we take the derivative, we will get 1 over 1 plus x squared. Okay, and I think we can try something in 1 over 1 plus x squared, right? So probably we start by taking the tangent inverse x, and then take it into an integration form of 1 plus 1 over plus x squared. So this is, if you want to look more detail, then we can have this series of this will be from 1 and negative x squared plus x4. Okay, so we can integrate this series. So integrate. Okay. Let me write a constant plus x minus okay. Similarly, we find the constant by taking x check when x equals 0. So tangent inverse 0 is 0. Zero plus c, right? So constant is 0. So therefore, our tangent inverse x is equal to x minus x cubed over 3 plus x with power of 5 over 5. And now we can also rewrite in terms of series. If you remember that this is, we can write from this one. We can integrate this, okay, and we can also get the same series with this. Okay. It starts with, if we look on the power or the n, it's an odd number, right? So we can have 2n plus 1 or 2n minus 1. But let's just write 2n plus 1 so that we can have the alternate series x 2n plus 1 over 2n plus 1. So this is the tangent inverse x. So now we have some functions that we can represent as a series. Now this is a little bit advanced and a little bit complicated. If you miss out like the beginning of this introduction, you will miss out on how we are getting this. Okay. So if you look back, okay, the idea behind of this representation is we are taking this 1 over 1 minus x. This is the very basic idea. And from here, we can actually derive and integrate. Which means, if you have these expansions like this one, we can also derive and integrate this. And then we look on other functions as well, and we can relate those functions into this structure. We can also think on how we can derive and integrate those functions. Okay. So we have several functions like the ln, which is I think pretty obvious for ln because it has 1 over the function if we integrate. And then the tangent inverse also, it will be quite obvious because it will have a relation with the 1 over 1 plus x squared. And for the tangent inverse, if we just try some x, okay, we can extend x. If we want to try x equal 1, okay, we want to try x equal 1. Okay. There is an interesting phenomenon, okay? So when x equal 1, okay? Now this will be pi over 4, and this will be 1. If you try to compute to several n and try to solve this will result in we call this the Leibniz formula for pi. Leibniz formula for pi. So we can actually take the pi and take it into a series. So there are several ways to get pi. One way is going through here. maybe giving more example, okay, to let you familiarize with the relation between series and the functions. Okay. I think I can give you some examples. Okay. Find power series representation and find interval of convergence. Let me check the question. So let's just take some time to review the representations. Let me write the first one, okay? Let me write the first one. Okay, so first, we want the top equations to be just one. Okay, so we can factorize x squared and maybe factorize 16. Okay, so we will have this will be 1 plus the x4 over 16. Okay, or maybe and then from here, we will have 1 minus, okay. So minus, let me write in terms of x over 2 and then with power of 4. So these functions will be equal to x squared over 16 and then the sum of this negative x over 2 with power of 4. Okay, so we can write this as, first. And then power of n. Or if you want to make it more more clean and separate the alternate series, so we can write this is x. We can multiply inside x squared, multiply with the other x. So we will have, so separate the negative 1 with power of n, x with for n plus 2, and this will be 2 with power of 4n, and multiply with the 16 is 2 with power of 4, this will be plus 4. Okay. So by looking at this, we can see that it has the ratio x over 2, right? Negative x over 2. So we know that it will be converge when negative x over 2 with power of 4 is less than 1. Which means that this is actually x over 2 equal 1, or the radius will be 2. So radius is 2, and the interval of convergences will be negative 2 to 2. Okay. Now try to deal with the second question by yourself. And also I will give you more questions. Find power series representation for the function and determine r, or radius of convergence. First one is f of x is x 1 plus 4x squared maybe going down here. F of x is x plus x. Okay, we will discuss next Friday for this one. At least let me give you some advice, okay, on how we are going to deal with these three questions here. So the idea is we need to remember 1 over 1 minus x first. And when we look at on this we need to think whether we can have some functions that is maybe when we derive or integrate that is similar to what we have here. Okay. That is the first one. So you need to have maybe to deal with, so at the very beginning you need to deal with some derivatives, some integrations that you need to think whether you can find this form or not. Okay? So that's the first one. And the second approach is connect the relations with 1 over 1 minus x. Okay? That's the thing. And for some functions that I think we already deal with the examples. If you look on the examples, like the maybe from here, this type of example, 1 over 1 minus x squared, and you know that this is related to derivative. Okay. You can remember how we can deal with this, and especially when we have this ln 1 plus x, okay, x to the power of n over n. Tangent inverse, this will be x to n plus 1 over to n plus 1. Both of these may occur most of the time. So if you're getting used to this too, you can exchange whether when in the future you will encounter with this, you can exchange directly to this, okay? To shorten your time. So that's my advice. Okay? But whenever you maybe feel you don't really remember how to get this, and you can start from here. But to shorten your time, maybe you can just take some of the ln and this tangent inverse and exchange directly. I think that would be better to shorten your time. And this this representation of functions, and also later you will learn some of its applications. You will, I think, in 1 or 2 years, if you take some courses that related to advanced engineering, okay, any type of course, whether it's chemical engineering or mechanical engineering or whatever on the course, you will eventually get into the series. Okay, so if you don't get it now, then because if you're senior, I think still asking what's the representation function means he forgot on the freshman level. So yeah, at least you know how to represent the functions without power source. Okay, I think that will be our class for today. Next Friday I hope we can finish. So by Monday we can review all the chapter 11. Okay.